These are the lecture problems for Chapter 8. Take a second to read the problem. I'm asked to solve for the impulse. So J, I'm going to put a subscript Y because all my motion is in the Y direction for this problem. That's going to be equal to the final momentum minus the initial momentum, where I know that my momentum is going to be equal to my mass multiplied by my velocity. I know that the ball is stationary just before it is hit. So the initial momentum, P1, is going to be equal to 0. So I can take this guy and set it equal to 0. Now to solve for my final momentum, which is after it has been hit, that's simply going to be the mass of the ball multiplied by the velocity just after it has been hit. I don't necessarily know what this is, but I know that the ball rises up to 5.5 meters. So what I can do is I can actually use energy conservation. I can say the ball initially has some kinetic energy. It's going to go up to a certain height where it's stationary. At that point, all it has is potential energy. So I can say 1/2 mass velocity squared. This velocity is going to be my velocity 2. Is going to be mass times gravity times height of the ball, which I know. So I can simply cancel these two guys out, multiply by 2 and take the square root, and I'll solve for velocity 2 must be equal to the square root of 2 times gravity times the height. So I go ahead and I plug all this stuff in. 2, 9.8, and 5.5. And I come up with my second velocity, or better yet, V2, to be equal to 10.4 meters per second. So now I simply say that my impulse is going to be the mass of the ball, which I know. I do need to put that into kilograms, so that's going to be 57 times 10 to the minus 3 kilograms multiplied by 10.4 meters per second. And at the end of the day, the impulse that I put, the tennis racket put to the ball is going to be 0.593 kilograms meters per second. Okay, take a second to read 820. This is a conservation of momentum problem where we have a ball that is traveling towards a person at some velocity. I'm going to call that VB1, velocity of the ball, 1 indicating before a collision has occurred. Here we have the person. They have some mass, and the velocity of the person before the collision is actually going to be equal to 0. After the collision occurs, the person is going to have caught the ball. Draw it kind of like that. This system is going to have a mass of the mass of the ball plus the mass of the person, and it's going to be moving off at some unknown velocity, which we're going to solve for. What I can do is I can say that the momentum before the collision occurs must be equal to the momentum after the collision. And when I'm writing my velocities, I'm going to take care to say that the direction that the ball is traveling in initially is going to be the positive direction. So the momentum beforehand is going to be the mass of the ball multiplied by the initial velocity of the ball plus the momentum of the person. The person is not moving. They have 0 velocity, therefore they have 0 momentum. afterwards, the momentum of the system is going to be the mass of the ball plus the mass of the person, and they're going off at some velocity that I'm looking to solve for. So to solve this guy, I simply divide both sides by this quantity right there. So the velocity of the system afterwards is going to be the mass of the ball multiplied by the initial velocity of the ball divided by the sum of the two masses, ball plus person. And we know what all these quantities are. The mass of the ball is 0.4 kilograms. The velocity of the ball is going to be 10 meters per second. And the mass of the ball, 0.4, plus the mass of the person, 70, is going to give me a total mass of the system of 70.4 kilograms. Sum these guys up, and turns out that you're going 0.0568 meters per second. So you're moving, but you're not moving very fast because the ball didn't weigh a whole awful lot. For part B, where the ball bounces off your chest, I can leave the setup the same. The ball is initially coming at you with some velocity, but now I know that the ball has bounced off of you. Now it's traveling in the negative direction with some velocity that I know. This is velocity v2, the 2 indicating it's after a collision has occurred. And now we have the person moving off at some velocity v_p2. This is what I'm interested in solving for. The momentum before is simply going to be what I wrote before. It's going to be the mass of the ball plus, or multiplied by the initial velocity of the ball plus 0. The momentum afterwards is going to be the mass of the ball multiplied by the velocity of the ball after the collision has occurred, plus the mass of the person multiplied by the velocity of the person after the collision has occurred. So I'm going to solve this guy for the velocity of the person now. So I'm going to say that the mass of the person multiplied by the velocity of the person at 2 must be equal to the mass of the ball, initial velocity of the ball, minus the mass of the ball, and then final velocity of the ball. I'm going to divide both sides by mass of the person here, and these guys are going to cancel out. Now it's a simple matter of plugging it in, being very careful to remember that the velocity of the ball right here is going to be in the negative direction. So the velocity of the person is going to be 0.4 kilograms multiplied by 10 meters per second. That's in the positive direction. 0.4 kilograms multiplied by negative 8 meters per second. Again, the negative means that the ball is traveling in the negative x direction. And then the mass of the person is going to be 70 kilograms. So we go ahead and we solve this guy, and we come up with a velocity of the person to be 0.103 meters per second, and that's about double the velocity we found in part A. That makes sense to us because the ball has conveyed some momentum to you when it collided with you, and then you gave it some additional momentum when it bounced off of you. Momentum has got to be conserved, so you are going faster. Okay, take a second to read this problem. What I'm initially looking for in part A is this height that this ballistic pendulum is going to go up, and I know that I can apply energy equations to say that the kinetic energy of the block plus, or the bullet plus the weight is going to all go into potential energy at the top of the swing, which is going to be mass times gravity times this distance y. to solve for this kinetic energy, obviously I need to know how fast that it's going, and I can apply momentum conservation to figure out what that is. So what I want to do is I want to write my momentum before the collision is going to be equal to my momentum after the collision. Initially, I have my bullet that's moving and my block that is not, so my velocity of the block is going to be equal to 0, or velocity W is equal to 0. So beforehand, I'm going to say I have a mass of a bullet multiplied by a velocity of the bullet plus the momentum of the wood, which is going to be 0. All of that guy is going to be equal to the mass of the bullet plus the mass of the wood multiplied by this, by the combined velocity of the two. I'm solving for the combined velocity of the two, so simply v2 is going to be equal to the mass of the bullet multiplied by the initial velocity of the bullet divided by the sum of the masses. And it's a simple matter of plugging all of these guys in, converting everything into kilograms. So the mass of the bullet is going to be 0.012 kilograms, and it's traveling at 380 meters per second. The mass of the bullet plus the mass of the wood is going to be 6.012 kilograms. And we go ahead and we peck that into our calculators, and we're going to solve, say that the velocity 2 is going to be equal to 0.758 meters per second. Now I can apply my energy conservation, say 1/2 mass of the bullet plus the wood multiplied by this v2 squared is going to be equal to the mass of the bullet plus the wood multiplied by gravity multiplied by this height that it rises to, y. I cancel my masses out, and I solve for the height that it rises through, which is going to be 1 divided by 2g multiplied by v2 quantity squared. So 1 divided by 2 times 9.8 multiplied by 0.758 meters per second quantity squared, and the height that it rises up is going to be 0.0293 meters, or 2.93 centimeters. Now for part B, what I'm asked to calculate is I'm asked to calculate the initial kinetic energy of the bullet, which is going to be pretty straightforward. Kinetic energy of the bullet is simply going to be 1/2, so part B, mass of the bullet multiplied by the velocity of the bullet squared, so 1/2 multiplied by 0.012 kilograms multiplied by 380 quantity squared, and the kinetic energy of the bullet is going to come out to be 866 joules. In part C, I'm asked to calculate the kinetic energy of the bullet and the pendulum, or the bullet and the wood, in which case kinetic energy of the bullet plus the wood block is going to be 1/2 mass of the bullet plus wood block multiplied by v2 squared. So 1/2 multiplied by 6.012, got a good parentheses, multiplied by 0.758 quantity squared, and my kinetic energy of the two of those is going to come out to be 1.73 joules. Kind of what I'm looking at here is the bullet lost a lot or a lot of energy was lost in this system, going from the bullet to the bullet plus the block, into friction, into heat, and all that. I mean, we've lost 864 joules of energy to that. Remember, this is an inelastic collision, and so we cannot write conservation of energy.